here is the review for exam 4, and we start with chapter 12, which is fluids. All right, the fundamental formula that you have to know is that density is mass by volume. Everybody knows that. And the unit of density is kilogram per meter cube. And if you're given something in gram per centimeter cube, to change it into kilogram per meter cube, you need to multiply by 1,000. Okay, so density is mass by volume, and you've got to change it into kilogram per meter cube. Next up, pressure. Pressure is force by area. Pressure is force by area, and the unit is, of course, pascals. And then if you're talking about pressure exerted by a liquid, or a fluid rather, it would be, there's the unit, Newton per meter squared at pascals. H rho G, pressure exerted by a fluid is the product of the depth or the height, density, and acceleration due to gravity. Now remember that there are two types of pressures. One is called the gauge pressure. That is the pressure that's measured by a gauge. But you got to add the atmospheric pressure to the gauge pressure to get the absolute pressure. In other words, absolute pressure is the total pressure. So to get the total pressure, remember to add the atmospheric pressure to the gauge pressure. And the atmospheric pressure is 1 atm, but in physics you've got to have it as 1.013 times 10 to the 5 Pascal, or 101.325. So that's the atmospheric pressure. Yeah, that would be a good idea if you memorize that number, but I'll still give it on the exam. And then Pascal's principle, a liquid transmits pressure equally in all directions, and we're going to use that in the case of, remember I told you about a hydraulic bench, hydraulic press, hydraulic jack, didn't I? That's the same idea used in the brakes of automobiles. So F out by F in is equal to area out by area in. That means you're able to magnify the force. Because remember when I taught you about the two cylinders that have different areas, and you apply a small force on the smaller cylinder, you will get a big force on the bigger one. If this ratio is, let's say, 100, then you're going to get 100 times the force that you apply. Okay, that's the idea of a hydraulic. So that's chapter 13. There's more. Buoyancy, buoyant force. What do you mean by buoyant force? I mean, it doesn't sound good if I keep talking like this. What is buoyant force? Remember, formula for force of the liquid pushing up is always the product of the volume of the fluid displaced times the density times G. So remember, that's the volume of fluid displaced, the density of the fluid, and G. And I think I did not teach you this equation of continuity, did we? No, so don't worry about that, but it was already on the screen, and this is Bernoulli's principle, which I didn't teach you too, so. But it's such a, I mean, it's cheating you if I don't tell you something about Bernoulli's principles. Just, so there. Pressure, P1 plus 1/2. You know that's the density. Velocity squared. Yeah, density of air. Yeah, density of air. Velocity squared here. Plus, again, the same. But this term, remember, there are three terms here. This is potential energy. This is kinetic energy. This is pressure energy. All right, let me write that down in a different way. You are going to see that. It takes only 3 minutes. What's the formula for kinetic energy? Kinetic. Okay. Let me use a better pen. 1/2 times mass times velocity squared. Now, if I divide this with a volume,
you get density.
So now I'm getting the kinetic energy of 1 meter cube. See how that works? Because mass divided by volume is density. That's it. So that's the kinetic energy of 1 meter cubed. Now, potential energy is mgh, isn't it? Mm-hmm. If you divide that by volume, once again you get rho g h. Instead of h, I've used y. Who cares? I mean, it's just height.
So I take it they use the same kind of thing, not only for flying, but for stuff underneath the ocean?
Kind of. Actually, even more than that. Once I finish that term, I'll come to a little bit more discussion. And the first term, this one, is pressure energy. And does anybody remember that work done is pressure times volume? So if you divide by volume, what do you have? Pressure.
So pressure is work done is pressure times.
Yeah, so all these terms are for 1 meter cubed. Just remember, 1 meter cubed. So the first term is kinetic energy, pressure energy of unit volume. It's kinetic energy of 1 meter cubed. Potential energy of 1 meter cubed. So what is Bernoulli's principle? The total energy must be a constant, that's all. And what does that mean? Doesn't that mean that if this term decreases, then this term has to increase? Come on. Because if the total has to be the same, what does it mean? Where the speed becomes higher, the pressure has to be there. That's what I'm telling you. And another application of this is in baseball. When you throw that spinning ball fast, it curves. Bernoulli's principle. How does a spinning ball curve? All right, how is it easier to spin a ball? 12. Now chapter 14, Oscillations, which we did just 2 days back. Oscillations and the important lab that you did. You remember the lab, time period and all that? All right, the formulas in oscillation. F is equal to kx minus kx. K is the spring constant. F is the force in the spring. X is the displacement. Then acceleration is given by minus k by mx. So that is the general equation for simple harmonic motion. That is acceleration. And you know how to get this formula from here, right? Because force is nothing but mass times acceleration, right? So that's m d squared x by dt squared. And then all you got to do is switch sides and divide throughout by the mass. And that is a second order differential equation. Have you heard of a second order differential equation? Yeah. And what's the variable here? Of course, time is a variable. X varying with time. Yeah, X is a function of time. Okay? These are constants. Both these are constant. One is spring constant. The other is the mass. Since X is a variable, its solution is given this way. X is the variable. All right. What's A called? Amplitude. Omega, now you know, actually omega is square root of k by m. I'm going to prove that. And this is called the initial phase. You know that. The equation for velocity is omega root a squared minus x squared. I do not know if I've written the equation for maximum velocity, but you know it happens at the equilibrium position, isn't it? And it's going to be a omega. I think, yeah, I have a omega. Because at the equilibrium, x is 0. Okay, that's why you get square root of a squared is a omega. So remember that. So that's chapter 14. Some more to come, I'm sure. Again, acceleration is this, and I had written that before. The maximum value of that would be minus omega squared a, because x becomes a, this becomes maximum. So if you're asked for maximum value of acceleration, that's the formula. Then you have time period of a spring, oscillations of a spring, 2 pi m by k. And then for a simple pendulum, you have 2 pi L by g. This is what we did in the lab, correct? That's where you found the K. This is for a simple pendulum. And then the energy of oscillations is 1/2 Ka squared. Total energy. That's total energy of an oscillator. 1/2 Ka squared. And A is the amplitude, of course. Kinetic energy. What's the formula for kinetic energy? Not 1/2 mv squared here, okay? It's 1/2 K A squared minus x squared. Potential energy is 1/2 kx squared. Oh, obviously, when you add these two, that's what I've put there. You know, when you add kinetic and potential, you get the total. See, that's what this arrow shows. If you distribute this and add it to this, these terms will get cancelled, right? The negative and the positive, 1/2 kx squared. So that's total energy. That is chapter 14. 17. I don't think I'm going to ask you to change Celsius into Fahrenheit, but yes, this is the formula that you need to change Celsius into Fahrenheit. And to change in the other direction, you have to be very careful. You see the difference, don't you? You see the difference? Got to first subtract 32 and then multiply by 5 divided by 9 to change. Expansion. What's the formula for expansion? Change in length is this. Alpha is a constant called linear expansion or linear expansivity. Original length, change in temperature. Change in volume, same formula, kind of formula. But does anybody remember the relation between alpha and beta? Yeah, beta is 3 times alpha. Cubical expansivity is 3 times linear expansivity. So keep that in mind. And Boyle's law, that is Boyle's law. Pressure times volume is a constant. We used it today. Next, you have Charles' law. Pressure by temperature is a constant. Yes. And again, volume by temperature is a constant. You need to know that. Then the ideal gas equation. Oh, I'm writing the beta is 3 times alpha there. Yeah. In the ideal gas equation, I just want to ask you, what's this? Number of moles. This is a constant. It will be given to you. 8.314. Does anybody remember the volume occupied by 1 mole of any gas at STP? Mangoes? Liters. Okay. We want it in meter cube. It will be 0.0224. Yeah, meter cube. What happened? Don't remember? Oh. Okay, here it is. 1 mole at STP is 22.4 liters. It's always an easy way out. Avogadro number, in case you don't know what it is. That's the Avogadro number. What do you mean by Avogadro number? The number of molecules in 1 mole of any gas, isn't it? It'll come back and bite you if you don't know all this. Chapter 18. Now, good to know. I'll give you all the cons. I know why Roberto's laughing. He'll say, yes, good to know that. Pressure exerted by a gas. Or give me the terms. Pressure exerted by a gas. What's that? What is that? N can stand for nothing, but that's not what it is here. It's the total number of molecules. So when you use caps N, it's the number of molecules. If you use the little n, it's number of moles. Caps N is the number of molecules. This is the mass of a molecule. Mass of a molecule. And that is the root mean square velocity. Okay. Average kinetic energy of a gas is 3/2 kT, where K is called Boltzmann's constant. Average kinetic energy of a gas. There are a lot of K's, yeah. And this K is another constant, Boltzmann's constant. It's the ratio of the universal gas constant to the Avogadro number. I might be writing that later on. All right, this is root mean square velocity. I'm going to give you two formulas. It's on your formula sheet, 3 times P by rho, pressure and density. The other one is square root 3 RT by the molecular mass. What did I do? Oh yeah, I was just trying to say that the K there, Boltzmann's constant, is the universal gas constant divided by the Avogadro number. That's what it is there. Yeah. Don't worry about TC, PC, and VC. Those are the critical constants. Not much time to talk about those. (19). A very important chapter, 19. Heat lost or heat gained is MC delta T, where you have the mass, specific heat, and change in temperature. But if it's a phase change, then it's mass times latent heat. And if you mix a hot object with a cold object, then heat lost is equal to heat gained. Haven't we done so many problems on this? Heat lost is equal to heat gained. The one thing you have to remember in those problems is that when you take the difference, the higher temperature must be first. You have to think about it and then put it there. This is the first law of thermodynamics. Change in internal energy is equal to heat entering minus the work done. Change in internal energy is the heat entering the system, take away the work done. Change in internal energy is the heat entering the system minus the work done by the system. Heat entering the system is dQ. Work done by the system is dW there. Okay. And again, this I had no chance to teach you this isothermal process. The work done is nRT, natural log V2 by V1. It's just from the last semester, so you don't need that. And again, work done in an adiabatic process is this. Neither do you need that. So I'm not going to question you on those two. Okay, I'm going too fast. For an isothermal process, pressure times volume is a constant. For an adiabatic process, actually there are 3 equations. I gave you 2, I think. Pressure times pressure volume raised to gamma is a constant. We even did a problem. The next one is TV raised to gamma minus 1 is a constant. Okay, I only wrote down 2 here, so it's fine. If you take 1 mole of a gas, and didn't I tell you that a gas has 2 specific heats, Cp and Cv? If you take the difference between them, you will get the universal gas constant. This relation is called the Mayer's relation. Spelling is different a little bit. Mayer's relation. Doesn't that already show that Cp is greater than Cv? Come on, because when you take the difference, you get 8.314. It's all good for you to know. Thermodynamics is a big deal in engineering. Did you know that? There is a paper by that name. Statics is a complete paper you have to take. I mean, so all this is the bare basics that you need. So.
What is R?
Universal gas constant, 8.314. And this I had mentioned, the ratio of specific heats is gamma. And I had given you the numbers. 1.67 for monoatomic, 1.4 for diatomic, and 1.33 for polyatomic. All right, we are coming to the end, and if you have a question, please ask. I know I'm going fast, but then I need to give you time to prepare and study and all that.
Okay, what was the 1.67 for the ideal?
It's the ideal gas is monoatomic, so yes.
And then 1.4 is
Diatomic.
diatomic, and then 1.33 is
Polyatomic. More than two. More than two. So 1.4 would be for hydrogen, nitrogen. Helium is monoatomic, He. And then 1.33 would be for carbon dioxide, sulfur dioxide. Remember the rotten egg smell gas? Sulfur dioxide. All that. Chemistry is so interesting. All right. Conduction. The formula for conduction of heat is Q by T is Ka, difference in temperature by the distance. Now this is where we talked about heat coming in through the walls of the room and stuff like that, where T1 and T2 are the temperatures, outside and inside. D is the thickness, A is the area, K is, what's K? The constant, but it's called the thermal conductivity. That's where we talked about air being a bad conductor. Does anybody remember?
It's a perfect insulator.
A perfect insulator. And I don't know whether I mentioned birds fill their feathers with air and all that. I think this is where I talked about all that anyway. Radiation. Radiation, E sigma A, T1 raised to 4 minus T2 raised to 4. Where T1 is the temperature of that hot object, T2 is the temperature of the surrounding. So, have you wondered why sports people, for basketball, for example, once they are pulled out of the court, they immediately go and have something wrapped around them? Football players, even basketball.
to keep from the heat escape.
Okay, now why do you think more heat escaping at that time from their bodies? Yes, because the body temperature has gone up. See, I'm talking about this. That's the temperature of their bodies now. And remember, it's raised to the power 4. So even if their body temperature goes up a little bit, the radiation given out is much more because it's raised to 4. Are you getting? And that is the temperature of the surroundings. So especially if they're playing in a cold state or in a cold place, cooler place, if you don't cover up, they're going to be shivering in a small time because they're losing a lot of energy. That's why. And sigma is Stephan's constant, which is 5.67 times 10 to the negative 8. That's sigma. And I crossed that out to tell you that if nothing is spoken about the atmosphere or the surroundings, take that as
0.
Right. So if a problem says a particular object is, losing heat and you don't talk about the surroundings, just neglect that T2. That's okay. That is all there. I know. We still have formulas. Okay. Because I didn't talk about the Carnot's engine and all that. Q is the heat, quantity of heat given out. T is seconds. So if you take Q by T, you're going to get the heat given out in 1 second. Yes?
When do you cross out the T2?
If there's no mention about the surrounding. So for example, if you're given, calculate the heat given out by an object at 100 degrees Celsius. Again, remember, you have to change it into Kelvin. And also saying that, what is this? Okay, for a black object, 1. For a white, shiny surface, that is
0.
All right. So whatever is given, use that.
Heat specific. Whatever.
No, that is emissivity.
Amos.
Yeah. Okay, and remember, A is the area of the surface. The area of the surface, because it's the surface that's giving out the heat. Chapter 20, our final chapter, efficiency of Carnot's engine. Efficiency of Carnot's engine is work over heat taken in. Now there are 3 formulas for efficiency. Did I teach you all this?
Nope.
What?
Nope.
You also said to remind you didn't finish the 19.
Yep.
I finished 19 now. I didn't teach you chapter 20, you know?
No.
Okay. Let me continue the review and then teach you, because this is on YouTube. You know what I mean? I can't break it now. I'll teach you. Work over QH. Work done by QH. QH stands for heat from the hot object. Heat absorbed from the hot object. But there are two other formulas. I'll let them run. That's all those three formulas of our heat engines. I can continue recording. All right, the COP of a refrigerator is QL by work. That is there. The second formula in terms of quantities of heat, and the third in terms of the temperatures. That is the COP, the coefficient of performance of a refrigerator. Yes. So actually you're producing heat by burning gas, natural gas, and the heat that you get, you pump it into the house. That's it. So you're not taking anything from outside because it's very cold outside, obviously. And you're recirculating that, heating it, keep on heating it, and keeps the inside. So the change in the definition of the COP, you can see now. Please watch this for a refrigerator. The only difference is, instead of QC, it'll become QH for a heat pump. You know what I'm trying to say? It's still reverse, but because you're giving heat in, it's QH by work. And then the other two formulas naturally come in. Natural. Simple. That's a heat pump. And the last topic is change in entropy.